Hello everyone, I'm Dom, M0WUF, and some of you have been asking me about the equipment that I've been using to experiment with the QO-100 satellite recently, so I thought I'd put together a little video to explain what I've been doing. But before we get stuck into the equipment, let's go inside and have a little look at some of the theory behind the satellite. QO-100 is an amateur radio satellite launched at the end of 2018 and which has been operational since February 2019. Now, of course, radio amateurs have been building, launching and communicating via satellites for decades. So what's novel about this one? Well, it's in a geosynchronous orbit. All previous amateur radio satellites have been in low Earth orbits, which means they rise and set and you have to track them across the sky. Often they'd only be above the horizon for perhaps 10 minutes or less. QO-100, on the other hand, is geostationary, meaning that it appears to be in the same point in the sky all the time because it follows the Earth's rotation. Geosynchronous orbits are really expensive. Slots are limited because there's only a small belt where you can put the satellites, and consequently there's high competition for them. All the broadcast and other commercial communication satellites all want to be in a geosynchronous orbit because, well, you wouldn't want to have a motorized satellite dish on the side of your house, and even then to only get TV pictures for a few minutes every couple of hours, would you? So how has QO-100 got one of these precious positions? Well, QO-100 is actually a couple of amateur transponders that are carried on a commercial broadcast TV satellite known as SHAL-2. It's a satellite that carries a lot of TV programs to the Middle East, operated by the state of Qatar, and it's Qatar that's allowed amateurs to add a couple of extra transponders to the satellite, and indeed the QO in the name QO-100 stands for Qatari Oscar. You'll remember that all amateur radio satellites are called Oscar, orbiting satellite carrying amateur radio. One of the results of being in a geosynchronous orbit is that the satellite is extremely high above the Earth's surface, giving a massive coverage range, extending from the tip of Brazil, covering the whole of Africa, Europe and the Middle East, the Indian subcontinent, and even as far as the west of Thailand. There's even a QO-100 station near the coast of Antarctica. Now, all of that coverage is accessible from a relatively simple setup and without the vagaries of HF propagation. By the way, if you're watching this from North America, sorry, you don't get to play with QO-100. It's below your horizon. SHAL-2 and the QO-100 transponders are located at a position known as 26 degrees east, which is to say if you were standing at the North Pole, standing on the Greenwich Meridian, the satellite would appear to be 26 degrees east of south. 180 minus 26 is 154, so the satellite would appear to be at an azimuth of 154 degrees from the North Pole. Here in the south of England, near the Greenwich Meridian, it's at an azimuth of about 147 degrees. Now, as I've said a couple of times already, there are actually two amateur transponders carried on QO-100. One of them is the narrowband transponder for voice and for narrowband digital communications, and the other is the wideband transponder for digital amateur TV signals. The principle of operation is the same for both, but as you'd expect, you need rather more power to use the wideband transponder, which I don't have, so I won't be covering it today. For both the narrow and the wideband transponders, they act similarly to crossband repeaters. The uplink, what you transmit onto the satellite, is at around 13 centimeters, so around 2.4 gigahertz. The downlink, what the satellite transmits back on, is on 3 centimeters, so around 10.6 gigahertz. Now, those bands sound scary to an HF operator like myself, but the useful thing is that the 2.4 GHz frequency is similar to Wi-Fi and Bluetooth, so there's loads of common equipment that can be repurposed. And similarly, 10.6 GHz is near enough the 11 GHz downlink frequency of broadcast satellite TV, so we can repurpose equipment there too. In fact, the main piece of gear you'll need is the 13 centimeter transmitter, but that can be easily and fairly cheaply sorted using an SDR or software defined radio. Make sure you get one that's capable of transmit at 2.4 GHz, as some only go up to 1.5 GHz, and I'll be showing you how I'm using the Line Mini SDR in just a moment. Unlike amateur repeaters that have a single input and output frequency, the QO-100 repeater it repeats a whole chunk of spectrum, 500 kHz on the narrowband transponder and a whole 8 MHz on the wideband transponder, which means many QSOs can happen at the same time. On the narrowband transponder, the band plan resembles that of an HF band plan, with CW at the bottom, then data modes, then SSB, and then there's this mixed mode and special purpose section at the top of the band. Please note that no transmission should exceed the 2.7 kHz bandwidth of a standard SSB signal, so you shouldn't be using AM or FM on the satellite. The low and the high ends of the transponder are marked with a beacon, and you obviously shouldn't transmit outside the frequencies contained between these two beacons. The higher beacon may change mode in the future. It's actually an experimental beacon. The low one is CW. In the middle of the SSB band, there's another middle beacon, which is the PSK beacon. All three beacons have a 5 kHz guard band either side of them, so you shouldn't transmit immediately around the beacon frequencies. The PSK beacon is a useful constant carrier source, which we'll use a little later on to stabilise our receive frequency. The PSK beacon also carries telemetry data about the satellite in the same format as that used by the AO40 satellite, so you can use the AO40 receive program to decode it. And it's advised you do periodically decode the telemetry data, because the mailbox may contain important announcements about changes to the band plan or other restrictions in force. You decode the band plan literally by feeding the audio of the PSK beacon to AO40 receive. The only other thing you really need to know about operating on QO-100 is that you need to be able to listen to the downlink while transmitting. Fortunately, that's easy with a setup like mine. 13 SEMs and 3 SEMs are far enough apart that you don't need any special filtering. Although hearing yourself with a fractional delay can be a little off-putting at first, the main reason is to ensure you aren't transmitting too much power. Your signal shouldn't ever be stronger than the 3 beacons. If it is too strong to the satellite, a siren sound will be injected on top of your transmission, so if you hear yourself coming back with a siren on top, you need to stop and turn down the power. Luckily, my setup isn't anywhere near strong enough to trigger that siren, but I have heard it on other people's signals a few times. Remember, we're effectively guests on this commercial satellite, and if we don't play nicely, we may not get a similar opportunity in the future. Okay, well that's the theory. How do you actually get going on the QO-100 satellite? Well, obviously we've got the dish here, but a lot of the magic is actually in this box here. So let's open that up and I'll talk you through what I'm using. Okay, so let's talk first of all about how receive works. Receive is probably the simplest thing to get started with. You don't even need one of these big 90cm dishes. 45cm mesh dish is absolutely fine for receiving here in the south of England. So the first thing is you need one of these, which is a standard domestic television LNB. The purpose of an LNB is normally to take the satellite's signal. Domestic satellite television tends to be at about 11 gigahertz, and what we want to do is to take that down to about 900 megahertz for domestic television, which is going to be a lot easier to send down coaxial cable. Your losses are not going to be anywhere near as high. Fortunately, the downlink from QO-100 to about 10.6 gigahertz is within the range of most of these LNBs, more or less, and we can then just get the signal down to about 730 megahertz. Now, I should say that everything I'm showing you here is just one way of doing it. It's absolutely possible, for example, to modify the LNB and get it down to the 70 centimeter amateur radio band instead. But I'm using a Line Mini SDR, which means I've got frequency agility. I can very easily just tune into the 730 megahertz where the LNB is coming out. What I would say is, if you're getting one of these, make sure you get a PLL LNB. There are a couple of types out there. For domestic television, it doesn't really matter how frequency stable the LNB is. The transponders are very, very wideband, very, very strong, and so frequency stability is not a major issue. When you're tuning into an SSB signal or a CW signal, PSK signal, your frequency stability is much more important. So a PLL LNB is definitely what you want. So normally your LNB would be mounted about here at the focal point of the dish. You'll notice that mine is actually back here. We'll come back to the reason why, but effectively that is just a standard domestic television LNB, and the coax that comes out of it is bringing me the QO-100 signals at about 730 megahertz, as I say. So inside my magic box of tricks, let's follow what happens to that signal. It's coming in on the coax here, and first thing it hits is going to be this thing here. This is a bias T, and all that's doing is that's supplying the 12 volt supply up to the LNB. The LNB is an active component and needs 12 volts. The RF is just passed straight through the bias T, so that's now going to go into the input into the Line Mini SDR. You'll notice I've added some heat sinking onto this Line Mini, and there's also a fan back here as well, and that's because the Line Mini can get very, very hot if it's working, particularly on transmit. The receive signal is then just sent down the USB cable. Where's that gone? It's down here, down the USB cable to the software for decoding. Now this is a USB 3 cable, gives much higher bandwidth than USB 2, it's what the Line Mini SDR uses, but you do need to be aware that the maximum length of cable that's specified in USB 3 is 3 meters, so that's going to limit where you can put your laptop relative to your dish, although obviously there are ways around that in terms of sending USB over things like IP. That's kind of out of scope for the moment. So that's all there is on the receive side. Let's take a look at the transmit side, and again the basis of it is again the Line Mini SDR. That's going to be doing our transmission. Coming out of the TX port here into this piece of cable along here, and that then goes into these two, one there and one there, little driver boards. These are SPF 5189Z chips, very, very cheap on eBay, and they're specified in theory up to 4 gigahertz. So these are just going to take the 10 milliwatts or so that comes out of the Line Mini SDR and just bump that up to about 150 milliwatts, which is enough to drive our main amplifier. So these are require 5 volts. The rest of this circuitry basically is a 12 volt circuit. So we've got a voltage regulator, where's it gone, back here, with a big heatsink on it, which is going to supply the 5 volts to those two driver boards. Now, one thing I got wrong when I first started playing with this kit is I started off by using an automotive step-down transformer from 12 volts to 5 volts. Yeah, not recommended. They're not quite good enough for this purpose, and my signal ended up with all sorts of sidebands and nasty effects on it, and looking at it in an oscilloscope was quite scary. So definitely want to use a decent voltage regulator for 5 volts. And thanks to M0WUT for pointing that out to me. So anyway, the signal, once it's come out of the last of these step down of these driver boards, goes into this piece of coax, which then on the lid of the device, just for cooling reasons, goes into the side of this. Now this is marketed on eBay as an 8-watt Wi-Fi amplifier. Now, two things with that. First of all, it's not 8 watts. We've had it open. The bits inside it, maximum it could possibly do is 2 watts. And you wouldn't want to use this on Wi-Fi either. It's not going to be type approved, and particularly in Europe, it's not advisable to use that on Wi-Fi. The other thing to know about these is, although they're very cheap, because they're designed for Wi-Fi, they have they're designed for a very fast transmit-receive changeover cycle, which isn't really suitable for use with SSB and CW. So easiest thing to do is that there's a very simple mod you can do, details in the description below, where you just put a small solder bridge between 2 pins on one of the chips, and that will lock it permanently into transmit, which is absolutely fine. You know, SSB and CW, there's not going to be a signal there if we're not transmitting, so we can lock the amp permanently in transmit. Signal then comes out of the amp on this piece of coax. This is going to be your main piece of coax going to your dish. So you want to make it as short a run as possible. We're at 13 sems here, and we've only got 2 watts. We don't want to be losing very much power, so keep it short and decent quality coax. Well, this stuff is CRF200, which is a Chinese clone of the LRF200, and fairly decent stuff. It's still, though, the 1.25 meters I've got here has a loss of about 0.55 decibels per meter, so I'm still going to be losing probably about half a watt or so of power by the time it gets into the antenna. So talking of the antenna, let's take a quick close-up of this antenna. It's a potty antenna, as it's known. It's a patch of the year antenna, and let's take a quick closer look at how that works. Okay, so here's the potty antenna, and I certainly don't claim to be an expert by any means on these microwave antennas, but so this is my understanding, is that this piece here is the driven element. The piece behind it, so this piece here, is the reflector, and the not quite circular cutout of the metal is what gives us the circular polarization that's needed for the satellite. This piece, by the way, is just a lens to help focus for the waveguide going back to the receiving LNB. By the way, the red bits here, and also there's a red holder that's just holding the waveguide into the LNB holder. These are 3D printed. There are designs out on the internet thanks to M0WUFC, who put together the 3D prints for me. Now, one thing I should say, just from a safety perspective, is that I wouldn't want to be standing right here when I was transmitting. Now, this, as I say, is a 90 centimeter dish, and the 2 watts that's produced at the patch antenna, by the time it hits this dish, which has got a gain of about 26 dBi, we're going to be looking at about 500 or so watts of ERP that's going up into the sky. So fortunately it's got a fairly high angle of takeoff, which means that by the time you get to the other side of the road, it's going to be way above the tops of houses, but I wouldn't want to be standing right here, as I say. The other thing I should mention is that by the time you're getting up to dishes of this sort of diameter, the larger the dish, the slightly more difficult it is to get it exactly bang on where the satellite is. It is just a pinpoint in the sky. So if you've got a 45 centimeter dish, it's going to be quite easy to find that signal. It's not quite so directional. At these big diameters, certainly if you're getting up to the sort of 1.2 meter diameter dishes, which you're going to need to do if you're going to get onto that wideband transponder, then you're going to be needing to have very, very precise alignment of your dish. Now, one very annoying thing to just be aware of with these Wi-Fi amplifiers is that, like most Wi-Fi equipment, they on one side use reverse polarity SMA. So this is the normal RF input to it, and that is a normal SMA socket. So that's an SMA female. It's got the socket, it's got the thread on the outside ring, whereas on the other side, the RF outside is a SMA, a reverse polarity SMA, or RP SMA. This is actually the female RP SMA. It's got the plug in the middle, unlike what you'd normally find with a female. So this is an RP, a reverse polarity, but it has that screw thread on the outside as well in the female. Really important to be aware of this. It completely threw me at one point when I tried to connect together a patch lead, one for a female SMA into a male SMA, RP SMA, and the result was that there was actually no central connector at all. Okay, so I've now come back inside and we're ready to start setting up the Lime Mini SDR with SDR console. So to do that, first thing I'm going to do is to click on definitions and then search for my Lime SDR. It has been found, that's good, so we'll add it to the list. Now I could just leave it like that, but if I do that I'll have to keep track of 3 frequencies at all times. There'll be the 3 centimeter downlink frequency, there'll be the frequency I need to tune into, which will be after the LNB has down converted it to about 730 megahertz. And then there's also my 13 centimeters uplink frequency. That's quite a lot of frequencies to keep track of at all times, so it's a lot easier if SDR console can just show you 3 centimeters downlink frequency, and that's the only one you need to worry about. And we can do that using this converter selection option. So we'll turn that on, and you see I've already set this up here. Now the TX side, we're going to need an RX and TX one. The TX side is the easy one. 8.089.5 is the TX frequency. That is that's the offset between the 13 centimeter uplink frequency and what it then comes back down on 3 centimeters. The RX converter is the offset, which is your local oscillator frequency of your LNB. This can be a little bit variable. It tends to be 9.750.2 or 9.750.0. As you see, mine here is 9.749.9. As I say, it is variable. The only way you can actually find this out is trial and error. So what you'll need to do is, when we come on in a moment to synchronizing to the PSK beacon, if you don't see the PSK beacon come up in the bottom half of the screen when we do that, that will suggest that your local oscillator frequency here is wrong. You'll need to come back and change it. So let's save that for now, and we'll save that. We'll select the Lime SDR Mini, and we need to select a bandwidth which is capable of transmit, because we want to be transmitting. The Lime Mini SDR only does 750 kilohertz bandwidth on transmit, so we'll go with that. So let's click start, and hopefully the rig should be found and SDR console will start receiving signals. As I say, I'm not actually plugged into anything here. I'm inside, so we don't actually expect to receive anything. A couple of other things we need to do to get SDR console ready to receive on Eshail, and the first of those is that by default it can only display frequencies up to 9.999 gigahertz, and of course we've got a 10.6 gigahertz downlink frequency that we're interested in. So we need to add an extra digit. That's very easy to do. You just go to View and Options, and then on the Spectrum tab, just allow a frequency range up to 99.9 gigahertz. That will add an extra digit on the next restart. Next thing to do is, we currently don't have a transmit panel, so we wouldn't be able to access any of the transmit features. We do that just by going to Transmit and then to DSP, and that's brought up our transmit panel. So just to show you around here, we've got on the left hand side, we've got our receive frequency, we've got the sound card that's being used to receive signals, and we can also set the modes and the filters that we are interested in. On the transmit side, we've got the transmit frequency. We can optionally choose to synchronize that with our receive frequency. You've got transmit mode, and again you can synchronize that so it's the same as your receive mode. Then you've got the TX button, which is what we'll be actually using to transmit with, and your drive. You'll want to turn the drive up, obviously, to get any RF out. Down here is where we'll select the microphone we're going to be transmitting with. So that's got us our transmit panel. The last thing to do is we'll need to synchronize our LNB with the geostationary beacon on the satellite. And to do that, we go to the View tab and to the Select More Options icon, and we're going to need to turn on the geostationary beacon. Now when I click OK, it'll want to restart the software so that it can add that extra icon to my toolbar to allow me to do that geostationary beacon synchronization. So let's click OK and restart. So the program's now restarted. I've got my geostationary beacon icon here, and I've got the additional digit for the gigahertz that's available to me. So it looks like we're all ready to go. Let's go outside and wire it all up. We'll need to connect in, of course, the laptop, a USB headset, and of course we need to put the top on the box of equipment as well. So now we're going to need to correct any drift in the LNB, and the way we're going to do that is by locking SDR console to the PSK downlink beacon, that beacon in the middle of the SSB spectrum. So I'm going to click on this on the View tab on the geostationary beacon, and what you get here is another little block opening up at the bottom of your screen, which includes, hopefully you'll be able to see fairly obviously, the PSK beacon. It's here at about 7489800 for me. If we now press the play icon over here, that will now lock everything, and you'll see that on the top half of my display all the frequencies have shifted. This now means that my frequencies are corrected for the drift of the LNB, and as long as nothing drifts too far, that will now stay locked. So that's about it. Let's give it a go.
Mike 0, Bravo Lima Foxtrot. This is Delta Lima 2, Quebec Bravo, here with QB.
Okay, Delta Lima 2, Quebec Bravo, Delta Lima 2, Quebec Bravo, from Mike 0, Bravo Lima Foxtrot. Very good to meet you. Nice to meet you, satellite, to about 5 and 8. 5 and 8. Name is John at Delta Oscar Mike. Delta Oscar Mike. And this is near the city of Cambridge. Cambridge in Juliet Oscar 02 Bravo Golf. Juliet Oscar 02 Bravo Golf. It's about to from Mike 0 Bravo Lima Oscar.
Good morning, Mike 0 Bravo Lima Foxtrot. Delta Lima 2 Quebec Bravo. I must apologize, I was not on your frequency when I called you first. Because I was not finished with setting up the VSO of my 2-meter transmitter. I was missing 200 hertz. I had the kilohertz fixed, but the decimals not. Okay, Dom. Thank you very much for the call. My name is Klaus. Kilowatt Lima Alpha Uniform Sierra, and QTH is Cologne. Charlie Oscar Lima Oscar Golf November Echo, and locator here is Juliet Oscar 30 Mike X-Ray. Juliet Oscar 30 Mike X-Ray. Been writing QSL cuts, doing some things, looking for a pen. Heard you calling, and then it had to everything had to go real quickly before you were gone. Okay, anyway, Tom, thank you. Mike 0 Bravo Lima Fox Delta Lima 2 Quebec Bravo.
And so that's QO-100 in a nutshell. If all of this sounds interesting but a bit too much investment right now, a great place to start is the British Amateur Television Club's web SDR. That allows you to listen to the satellite via the web without spending anything. You simply connect to a receiver at the famous Goonhilly Earth Station in Cornwall in southwest England. There's a link in the description below. And finally, of course, a massive thanks to a whole load of people at AMSAT, particularly AMSAT Germany and the state of Qatar, who've all made QO-100 happen. I've been really enjoying the satellite, and I hope you do too. I'm Dom, M0BLF. Thanks for watching.